my independent program. I had some other programs related to firefighter cancer. The main one that I was working on was on impulse noise, particularly from firearms. We really underestimate just how loud firearms are. The emphasis of my work was on risk communication of impulse noise and trying to help people understand what 171 decibels actually means.
Welcome to the SCL podcast, filmed in the MD Acoustics anechoic chamber at their testing facility in beautiful Gilbert, Arizona. Today, we welcome Dr. Robert Agnew, a seasoned EHS leader with over 25 years of experience in industrial hygiene, safety, and environmental compliance. As technical director at Liberty Mutual Insurance, he leads a national team focused on occupational disease risk and also serves as an adjunct professor at Oklahoma State University, where he previously researched firefighter health and protective gear.
Thanks for coming on the podcast, Rob. First thing I wanted to talk about with you is where do you kind of come from? Tell me about yourself and why did you get into industrial health and safety? Is that right?
Yeah, or industrial hygiene.
Industrial hygiene. I mean, I have a hard time believing that as a kid you sat there and thought, I care about hygiene at all.
Yeah, it's kind of a weird career, at least title. It's kind of archaic. Hygiene really means free from disease. It's kind of, in modern terms, come to mean clean, but really means prevention of industrial diseases. So silicosis from hard rock mining, or asbestosis from working in shipbuilding. And of course, what we're probably going to be talking about today would be hearing loss from industrial noise. And so my journey into that, I started in search and rescue in the wilderness and mountains, coastal ranges of California, some wildfire work. And that brought me to learn about Oklahoma State University, where I got my undergraduate degree in fire protection and safety engineering. I thought I was going to be a firefighter. And during my coursework, I got introduced to industrial hygiene, and it really attracted me because of the, protection of people, workers, a lot of technical science and mathematics and biology, physiology, toxicology, all of that mixed together. So I went and did my graduate work in industrial hygiene, and then went out and worked in the industry, and then after that, I decided to come back to OSHA as a professor for about a decade. While I did that, I did a PhD, kind of branching out a little more into environmental science, which was looking at chemical exposures into buildings from contaminated groundwater. And then all along through there, I've had an interest in acoustical noise, industrial noise, how it affects workers, mainly because I've seen the results of it. How many workers that later in life, I've worked in food service when I was in college, and people can't hear. They can't hear in a restaurant, they can't hear their kids. And so it's a really devastating occupational disease that really doesn't trigger in our minds. We think about, cancer being really scary, or an amputation or something like that, but hearing loss is really devastating. It's kind of a secret, and how it affects people.
So you went to OSU, you were there. How long were you a professor there? And talk to us a little bit about what you were doing, your research while you were there.
Yeah, I was with Oklahoma State as faculty for 10 years. And my main research program, my independent program, I had some other programs related to firefighter cancer. But the main one that I was working on was on impulse noise, particularly from firearms. We really underestimate just how loud firearms are. And really the emphasis of my work was on risk communication of impulse noise and trying to help people understand what 171 decibels actually means.
Tell us more about that. What does it mean?
So the issue we have with impulse noise is people at least have been shown these charts with decibels on them, and a quiet whisper is 40 decibels or something like that, and your lawnmower is 85 or 90, and then there's a rocket is 160 dB, and two things come to mind when I look at those charts, or maybe three. Uh, One of them is, how far away did you take the measurement? I mean, I don't stick my head underneath a rocket engine and listen to it. So,
Yeah.
so I don't know how relevant that is. I need to know where you took the measurement. Um, that's one. And the second one is that it is a logarithmic scale, and our human brains don't work in logarithms. So, when you say, oh, it's 90, I got my stereo at 90 dB, and oh, we're going to crank it up to 100. Oh, it's just 10 dB. Well, the human brain doesn't understand that's not 10 dB, it's 10 times the energy. And, when you're talking about now you're going to go up to 170 dB, well, now you're talking about a 70 dB increase, which even helped me with the math. That's like 100,000 times louder. Um, and so it's problematic in trying to communicate risk using a log scale. And then the third piece is that then some folks will, on those same charts, they'll add in um, a firecracker or a pistol or a rifle. And that doesn't make sense either, because the impulses are lasting just a few milliseconds versus a continuous noise source like a lawnmower is going to be putting out energy constantly. And so those two things, how they affect human hearing, are totally different. They're different uh, mechanisms of damage to the ear. And so we really can't compare them as an apple to apple. It's an apple to orange. And so the risk communication around impulse noise is just woefully inadequate, is kind of the conclusion I came to.
So you were there and you saw this, and is this because you saw the problem, the way that it was analyzed, or how did you just fall upon impulse?
So so before I came to OSU, I worked for Raytheon, was a major defense contractor, and we did a lot of impulse noise, a lot of things generate impulse noise in the military, and a lot of hearing loss in the military. It's the largest compensated occupational disease. And so when I came to OSU, and I was like, well, what's your research program going to be? I wanted to continue that work with impulse noise, particularly with military personnel. And so that's kind of the natural progression onto why I went into that research. And how I came to the revelation of this risk communication issue was just that, was trying to communicate it, and seeing people struggle with it, or hearing those pat answers, oh, it's only 10 dB, or oh, if I'm just going to go out and just shoot one deer, it's not that, it's okay for one. It's not like I'm mag dumping all day or something. And so there's just an obvious lack of knowledge about how damaging firearm impulses are.
Got it. Well,
that's interesting. So, in your research with impulse noise, I just want to geek out a little bit. This is an area that I'm very interested in. I love shooting guns. I love learning about it, and I'm a big acoustics nerd. What would you say is the most helpful metric for analyzing the damage for impulse noise? Are you talking about like the military AHAH model? Do you call that the AHA model, or just
the AHA model?
We call it the AHA model here. So yeah. Or the LAEQ, the 8-hour equivalent exposure level, or what are some of the more helpful metrics that you use in your profession to communicate that damage peak
risk?
There, we could go on and on. So yeah, we'd love to hear your experience here.
Yeah, so peak. Let's start with that one. Everybody wants to go to peak, and I get it, because you're trying to communicate risk, and a single number is easy to communicate. And so we like to say, yeah, that rifle report is 171 dB at 1 meter left of the muzzle, which is what the mil spec 1474E says where you should measure it. Okay, great. The issue when you just talk about peak is it doesn't capture the entire waveform and all the damage that's going to occur. The best analogy I have for that is if you go down to Texas, outside of Austin, near the Circuit of the Americas race course, there's a stretch of highway that has a speed limit of 85 miles an hour. And so you're within the limit if you stay under 85 miles an hour. And if we go look at OSHA, their impulse noise limit, or if we look at even the middle standard, the noise limit is 140 dB. Okay? And so it's kind of like a speed limit, like stay under 140 and you're legal. Well, let's go back to our highway. If I have a Prius traveling 85 miles an hour, and I have a 18-wheeler over-the-road truck that's fully loaded, it weighs 85,000 pounds, and it's going 85 miles an hour, they're both under the limit. However, when they hit your station wagon, the resulting damage is a lot different. And that's the issue with just looking at peak dB. So we want to look at that whole area under that curve or that waveform and look at what's the total damage related more to the total energy that's in that particular waveform. And so you mentioned a couple ways to do that. The AHA model developed by the Army Research Lab. And it's a very complex model, really trying to simulate all of the mechanical actions within the ear, from the eardrum through the ossicles, little bones in there that amplify sound, into the cochlea, and eventually to the stimulation of the hair fibers, the cilia in your inner ear. And so it's a very complex model. They spent a lot of time really developing it, and I think it is probably the gold standard. It's the one that we would like to see people use. But it's very complicated. You need some very good processing power. You need, to spend time really setting baselines and doing a lot of work to get that model to output its value. And those are in auditory risk units, ARU, which is great. It puts it into a single number, but that number encompasses all of the energy of the system. So in the alternative measure that the mill standard allows is called the LIA EQ 100 MS. Say that 3 times fast. But what it's looking at is it's looking at an impulse measurement averaged over 100 milliseconds or integrated over 100 milliseconds, A-weighted. And so in that case, your more, I would say, standard rather than laboratory equipment has the capacity to actually run that analysis. Now, most of your off-the-shelf stuff doesn't have a microphone that can handle it, but it, at least from a computation standpoint, is actually fairly straightforward. And so then you mentioned the 8-hour equivalent, which you can then do some mathematical gymnastics and convert that 100 millisecond into an 8-hour equivalent. And then from there, you can compare it to your equivalent energy dose that you're used to with an 8-hour workplace exposure. So I'm a fan of the LIEQ 100 MS because for most industrial hygienists, which are the people that are going to be out there doing a lot of this measurement outside of a laboratory, it's in the language that they use. Their equipment that they use is at least somewhat capable of doing it, and it converts it into something that they're used to when it comes to comparing it to an OSHA 8-hour equivalent dose. So that's where I tend to focus most of my work on trying to communicate how we can do these measurements.
At Liberty Mutual, which is where you're at now, how what are you doing there, and how does that relate to kind of all the overall?
Yeah, so Liberty Mutual is one of the largest workers' compensation insurance carriers in the world, particularly here in the U.S. And so I work in our risk control services group, and we help our client companies prevent loss. And that could be, it could be from fire, if they have a, property casualty insurance. It could be from auto, if we have an auto line. But in workers' comp, we're out there typically in manufacturing environments, working with those clients to help reduce noise in the workplace.
Okay.
And if they have noise, then helping them select appropriate hearing protection devices, things like that. We try to focus on engineering controls, going and making enclosures around loud noise sources, or switching out alternative materials to reduce noise. In the impulse area, a lot of it is pneumatics and pneumatic controls on machinery, and dealing with exhaust mufflers or rerouting exhaust so that's away from where a worker is standing. But then we do get into, I think, more intense impulse noises. We have clients that have security forces, and so they are, they have to go qualify with firearms. You also have people using nail guns. which are not as loud as a firearm, but um, they're right up against that 140 dB limit, particularly when you get into powder actuated tools that actually use a 22 caliber charge to actually shoot nails into things or other anchors. And so what I'm trying to do is take the knowledge from working in laboratory systems on impulse noise and understanding the limitations of the typical sound level meters and dosimeters that we used for OSHA compliance, and trying to bridge that gap in between the two by working with manufacturers to try to improve some features of their systems, like offering an LIEQ 100 MS, which most of them have the capability of doing. It's just not a feature a lot of people have asked for yet. And then the next challenge that's really going to be out there is going to be the microphones. How are we going to get a microphone that can handle a 75 dB background industrial noise, but then and be sensitive to it, but then also handle 160 or 165 dB impulse? With microphone design, that's a real problem. Audie Claver and her groups, they're working on a dosimeter with 2 different microphones to answer that challenge.
That seems like the solution to me, especially with MEMS fabrication technology. You can make them pretty small and just have 2 different sensitivities right side by side.
Right. Yeah. And hopefully the MEMS microphone technology will continue to improve, and it will be able to handle those higher impulses. Right now, diaphragm is the way to go. But here's an interesting tidbit on diaphragm microphones on dosimeters. You put them on the shoulder of a worker, and if they run down a flight of stairs, it'll accelerate the whole unit. And if you have a diaphragm mic, it'll start accelerating the diaphragm, and so you'll get 110 dB basically hallucinations because of that. Or if the microphone gets tapped, you get these really big peaks that are not real. Where the MEMS microphone is not sensitive to that. We've done some side by side testing with thumps and running downstairs and things like that, and the MEMS are performing really well in that challenging environment of putting on a moving person, whereas diaphragms have some problems with that.
So when you talk about this is all industrial. Do you have any experience? Because you were talking about, military, right, and or that kind of stuff. It reminds me. Do you have any experience with the U.S. military and kind of looking at those readings and stuff like that with them?
I haven't done like shoot house work with the military. I have been working with, like the M4 AR-15 platform and looking at how well we can suppress them using suppressors. And some interesting things happen when you put suppressors on those rifles that are gas driven firearms. There's a lot more noises going on than just the muzzle report. So you've got the muzzle report. You have the supersonic crack from the bullet coming out the end. You also have the gas ejecting out of the port when the receiver opens and the bolt comes back. And then the very interesting one is when the bolt slams forward back into battery, you're still getting about 138 dB at the ear from the mechanical impulse of the bolt slamming forward. So you've got a lot of noises going on. And that's where the really high sampling rates really help when you want to start doing analyses of that. And what's really fascinating is when you put a suppressor on the end of a gas rifle, it actually makes the breech louder. It increases pressure at the end, so you have more gas coming through the gas tube, so you have more gas coming out the breech, and then the bolt is going further back, and then so it's coming forward with a harder spring compression. And so while we're suppressing the muzzle, we're actually increasing noise back at the receiver. Net total is still better to run the suppressor, but there's still you still got to pay the piper, so to speak, in some other aspects.
That energy's got to go somewhere.
So it sounds like you spent some time looking at, like you said, the suppression systems and collecting that data in high sample frequency, right, in high rates. And I guess the question is how do you know that these little parts are the contributors to the overall, right? Like, can you walk us through? So, like, if I was a high school kid and you were to say, "Hey, I'm explaining this to you, right? We just looked at a single gunshot. here's how we, walk us through how you know that. Do you take slow-mo cameras in conjunction with your with your analyzers? Can you walk us through that?
Yeah. So a couple things on that. So one, distance is our friend. So we take measurements on how far the microphone is from the muzzle, how far the microphone is from the breech. And so from that, you get general ideas of which peak on the waveform, where did it come from because of when did it arrive, using the speed of sound as a constant in there. High-speed video work is also very helpful. And so you can see what's going on. The mechanical action of a gunshot is very rapid, and so it's hard to see these things. So slowing it down greatly does help. And then you can use multiple microphones to help you then triangulate and figure out where those signals are coming from. And then I guess the final piece there on why does it all matter is really you have to think about air as being elastic. And so what happens is when that shot happens, the air gets expanded, and then you get into this rarefaction where it's going to lower the density of air, and you get a collapse back together. And just like a bouncy ball will continue to bounce for several times, the air around you is doing that. And so that reverberation in the air, even though it's only happening in a matter of few hundred milliseconds, each of those pulses is over 125 dB. Your brain can't distinguish it, but your eardrum is just getting slammed back and forth by the elasticity of the air around that very sudden, rapid impulse.
That's awesome. So you have a really deep knowledge and understanding of impulse noise measurements, impulsive noise sources. I got to ask you this because it's sort of one of the louder topics for the everyman. How impulsive is a pickleball hit?
So I haven't actually measured one, which is kind of a shame. So I do have an impulse noise inventory. It's a whole poster I've produced, and I did not become aware of the pickleball controversy. My parents are 80 and they play, and I've gone out there and done it, and didn't really recognize that, because I'm used to gunshots, and firecrackers, and things like that. I didn't recognize that pickleball could be an impulse noise issue until some folks brought it to my attention and started kind of looking at it. And I haven't gone out and measured it yet. But what's going on with pickleball is not that the impulse itself is super powerful, and it's probably not something that's causing damage to hearing, but it's having psychoacoustic effects. And so I've heard a couple analogies. One is like the torture where they drop the water on your forehead over and over and over. These pickleball courts, if you live in a home near one, you're experiencing tens of thousands of impulse noises a day, and people are basically going bonkers. And so I spent some time thinking about this. Why are these little popping sounds causing so much trouble for folks? And we talked about you like firearms, so do I, but like hunting. And one of the things you do when you go hunting is you have to walk a certain way so that you don't break sticks. Because if you break a stick, it alerts everything around you that there's a large predator around. Right? Small furry animals don't break sticks when they walk. Big predators do. And so I think what's happening in this psychoacoustic effect with pickleball courts is it's the analogy if you're sitting in your tent around a campfire and you hear a stick crack in the woods, you immediately get a fight or flight response. And so I think what's happening with these residences around pickleball courts is that the residents are being put into a state of fight or flight continuously from the constant popping noise. Now, I haven't done research on that. That's just speculation on my part, but I'm thinking that's what's causing the real visceral response against pickleball courts in neighborhoods.
Now,
Interesting.
I do have a question for you in regards to pickleball, because it is a big hot topic that we've dealt with a lot. When it comes to measuring a pickleball, paddle and ball, would you go the same route to measure that as you would a firearm?
So in terms of like, would I pick?
Would you treat
like
it the same?
Would I treat it the same? I don't know if I would treat it the same, but I would want to treat it consistently. And that's the one thing that Mill Standard 1474E has done. It says you're going to measure this 1 meter left of the muzzle, 1.6 meters off the ground, so that you have this same reference point. Because as you know, if you move the microphone closer or further away, you're going to get a different answer. And so we need to have a fair playing field if we're going to measure, firearm system A against firearm system B, particularly when you're looking at, suppressor design. So if I were to go out and measure, a pickleball pop, I would want to set up a very consistent way where I've got a pickleball paddle, I don't know, at 45 degrees, 1 meter off the ground, held in place. I'm going to drop a pickleball up above at some distance down on it with a consistent velocity. I'm going to have the microphone at a fixed distance at a fixed or known sampling rate, so that I can then compare paddle A to paddle B or ball A to ball B by keeping as many of those variables constrained as I can.
I agree 100%. Like the need for like consistency is critical for any kind of comparison you want to make there.
For me, I'm thinking about the engineering control on, there's a lot of work going on trying to figure out how do you make a pickleball paddle and ball quieter. Not necessarily your case where you're looking at, the controls around a cord of building an acoustic wall or something like that. So yeah, there's kind of different things you're trying to do there. Are you trying to figure out, was a mitigation successful? And I don't, again, what's the measure of success? I mean, before it was, whatever pig it was, 100 dB, and now it's 80. Like, okay, well, you reduced it, but did that change the psychoacoustic impact or not? And I don't know. I don't think we have a criteria for the psychoacoustic impact. But if we're like doing product design, that's more the setup I was describing as for product design.
And we've brought pickleballs and paddles into our anechoic chamber right here, and we've done more of that type of approach. For a while we were working with USA Pickleball, and we were looking at the different specs that a pickleball paddle needs to pass in order to be approved by USA Pickleball. And it's very interesting, the different design constraints and how those will need to evolve in order to allow some room for something to dampen the effects.
If you look at pickleball, it was designed for, mainly a recreational sport for, folks that are elderly or older. And so you want a very high kinetic return on the paddle, so you don't have to swing very hard. And so that's going to lead to very high impulse when you use it. And so that's the challenge, is how do you maintain a high, return on the ball, the efficiency of that versus the acoustics that are made from it.
As Samuel's alluding to too, right? Like there's engineering design criteria to meet, and so if they're not going to evolve that, then it kind of puts it all back into just so many options in terms of mitigating that sound. Do you think, like you're saying, thousands of pops, have you, in your experience, besides, because it sounds like obviously firearms and maybe shooting ranges or that kind of experience, or if you're dealing with industrial hygiene, like you said, pneumatics, are there places where people are exposed to thousands of pops at a higher magnitude or even lower magnitude than pickleball, for reference?
So certainly the higher magnitude is going to be a shooting range, or a shoot house. And, we have zoning regulations for those. So, we tend not to put a shooting range in the neighborhood, but for some obvious safety reasons, from the actual projectiles. But if you think about it, if you were near a shooting range all day, you would have a very similar psychoacoustic response. It's a little different when you're the one actually out there shooting, because you're going into that environment with the notion of doing that. You're the one who has control over it. But if you're in a residential home, 100 yards away, and just that's how you get woken up every morning, and it goes all day, and then you're trying to have dinner at night, it's going to drive you bonkers.
Do you think it would desensitize you though? Because the reason I'm going to play devil's advocate, so I lived in Newport Beach for years. The number one noise issue was the airport, John Wayne Airport. Number one, it woke up, hundreds of thousands of people every morning, 7 a.m. You knew the flight was going off. Obviously, it's not impulsive noise, but the magnitude of noise was significantly louder, a lot lower frequencies. It could shake people's homes as the jets take off. I mean, I lived there for 10 years. I got used to it. Could I get used to pickleball?
I can't say that I actually know. I mean, I lived near a railroad track and I've stopped hearing a train. I think something that may factor into that is the frequency. That the trains and the airplane are low frequency. Pickleball is at higher frequency. It's going to match more of the stick breaking in the woods. And so that may not allow us to adapt to it nearly as well.
Interesting. Stick in the woods.
Stick breaking in the woods. No, that's interesting. How would you go about testing the stick breaking in a woods theory?
Yeah.
Just like, imagine you're back at OSU, you're a professor again, you landed a grant.
Well, I would certainly have a PhD in psychology on my grant before I propose.
I love it. We love that. Yes. Yeah. Okay.
Yeah. So that's really, I'm not a psychologist. You know, that said, I'm doing pure speculation on just my own experience.
Of course. Yeah. No, of course. Yeah.
But I think I have been a fan of involving psychologists in a lot of work in the industrial environment as well, and understanding workplace dynamics, understanding, again, risk communication, and how do you effectively communicate risks to workers so that they take action in protecting themselves. And psychology can really help with that. And when it comes to psychoacoustics, I certainly would not want to venture into that without somebody by my side who understands the brain a lot better than I do.
How would they know? Would they do like a statistical analysis? I mean, it's kind of one of those things. Like I think of like this. So we had one of the engineers for NASA on here that's talking about the Sonic Boom's X-59 aircraft, and they're going to go out this next year, right? And HMMH is a firm who won the contract with that in conjunction with a whole bunch of other folks below, subcontractors. They're going to go out and measure sonic thumps, right? And like, what's the impact to the community? Would that kind of play into this as well? Like, hey, let's go to these communities. Let's see. I feel like there'd be some bias there because like everybody that lives in the neighborhood that doesn't like pickleball would be like, I hate it. And folks who love pickleball, and make no mistake, like we were in a hearing one time, 74% of 5,000 people who lived in the community loved pickleball. They were like, oh, when I hear it, it makes me want to get dressed and go and play. Then you got the 26% who are like, I hear it and it makes me want to leave my house for the day. So like, I feel like there would be some bias there, but like, how would that play into that as well? Like that type of analysis, or, you know what I mean? Where they do sample rating?
I don't know about the sonic thump. Again, that's going to be lower frequency. But for pickleball, I think, again, I'm kind of speculating outside of my field here, but I think that cortisol levels would be the test I would look at.
Cool.
And see, take a control and take a treatment and look at cortisol levels before and after exposure to a day of the pickleball impulses. That's
a good way to do that.
That's interesting.
Yeah, I like that.
I'm a noise guy. I think of measuring noise. I'm not a health guy, so I don't think of like what health metrics or how would you even compare that?
We produced a paper that we just submitted for NoiseCon. It was led by Naomi and our staff and Samuel, who basically went out and did some other recreational noise in conjunction with like hammer hit, like a hammer strike on a nail, basketball, and basically trying to get as loud of an impulse as you could off these, as opposed to like your engineered, hey, let's drop it at a height and come up with that. And then we came up with a kind of like, and I'll let Samuel kind of go into that a little bit more, but like what we thought was, okay, because one of the arguments is it highly impulsive? Is it impulsive? Is it, there's like, and if you go back and you look at the ASA or the standards associated with impulse noise, what is, there's different definitions to impulse, right? So one thing we were trying to basically put to bed, we hope, at some point, is the incorrect terminology around what is an impulse versus highly impulsive, and that kind of stuff, because that can get misconstrued.
Yeah,
right?
Adjectives are dangerous.
Adjectives are dangerous. So, Sammy, do you just want to fill them in for 2 seconds?
Right, yeah. So we had like 5 different team members in here in the anechoic chamber just trying to hit the heck out of a pickleball to see like, hey, how loud can we get this thing? and we took a basketball outside because you can't really bounce a basketball on a fully anechoic chamber floor. It just
Doesn't
destroy
sound the
too
same.
many
Yeah.
destroy too many wedges, and these things are expensive. So anyway, we took a basketball outside. We had Matthew, our producer, 6'3", 240 pounds, both hands high above his head, jumping and smashing it on the ground, saying like, "Hey, how loud can we get a basketball?" And measuring at 3 to 6 feet from each of those noise sources, and comparing that with something highly impulsive that's delineated in the standard like a gunshot, and just like you were saying, decibels are logarithmic, and just the scale difference of these things
Massive.
is monumental, right?
The inventory I put together, and I'll send you guys the PDF of the poster. On one side, I put all non-firearm impulses. On the other side, I put a bunch of different firearms, and I put 2 scales on it. I put one in dB, and so it's a very kind of linear increase. And the other one, I use Pascals. Again, just looking at peak. This wasn't
okay.
looking at total like LIAQ 100 of mass. It's just looking at peak, and so that you can see when you use Pascals what these increases really look like. That when you look at the OSHA impulse noise limit or the WHO impulse noise limit for children, which is 120 dB, they're like just little blips at the bottom of this giant table, and the rifles are
Yeah,
way up
exactly.
there.
Yeah.
We got to communicate risk. Like this is like totally different when you're talking about a pickleball versus a rifle. And
Sorry.
the pickleball is not going to tear your eardrum.
No,
That's not what I was told. I had a paper criticized, and that's what I was told, was it was going to make you just as deaf as a gunshot. And I thought, no,
don't think so.
but
I
I digress.
Well, let me guess, it was reviewer number 2.
I do have a question for you, though. You talked about cortisol levels or other measurements of like sort of the human response to noise. I'm sure in the insurance world you have access to different types of data. Have you seen data like that type of human response data for other noise sources?
No, I mean, we use biomarkers and stress markers and other parts of industrial hygiene, looking at how like chemicals in your body, how do they induce stress on different systems, and we look at kidney enzymes, liver enzymes, and things like that. But I don't think I've seen one related to noise.
Interesting. So that would be a whole new type of study that likely hasn't been done yet.
That's a cool idea. I like the idea around that. Some of the problems I see with that is just like how much of our food is just inundated with chemicals too. It's just hard to like know, is it from Pickleball? I mean, I'm not the guy that's going to set up the standards or the testing measures, but like, is it food induced? Is it lack of sleep? Is it we have little kids, right? So we're just like, I mean, my cortisol
sleep.
Yeah, we don't get any sleep, right? And so then you got the business owners, and you got the work, and it just goes on and on, as opposed to maybe somebody that's retired and they're just camping out in the desert somewhere, you know what I mean? And
with all those confounders.
That's right. There's just so many different variables, but I love this idea of figuring this out.
You need a large N, really is how you solve for that. And good population selection, and so with a good large enough sample size, good enough statistical methods, I think you'd be able to tease out is living near a pickleball court increasing cortisol or maybe some other stress indicator. I think there's probably an avenue you can go down with that.
We want to invite other folks to kind of come up with some sort of way to evaluate that, because clearly the psychoacoustics and the issues regarding around pickleball is kind of high. It's kind of high on the list right now. It would be nice to know if there could be some sort of standard method or something else out there that would be proposed. And like you said, like it's not even close in terms of hearing damage to the ear, but
yeah, I mean, we come across some things like this in the occupational world as well. If you think about an office worker who has to concentrate, they're used to their quiet environment. An engineer who's got to work on his CAD design like that is a lot different than a worker out on the factory who's moving and
Sure.
about they're wearing hearing protection. It's like it's just those environments and the demand on the brain are different. But if you then put that office next to the power distribution room and there's a transformer in there putting out that 60 hertz hum, it will drive that engineer completely bonkers.
Yeah.
And it's not going to be over. It's not over any kind of OSHA limit or anything like that. It may only be 70 dB, but it just irritates it, and they get worked up about it. And what you see is the more you ignore it, or the more you say it's not a problem, the more agitated they're going to get.
Yeah, that's true. No, that's an interesting approach too. Like a lot of times we look at noise as far as decibel limits. We love a decibel limit because it's like a speed limit. You can know pass or fail, right? But a lot of times, a lot of what we run into in these nuisance cases are things that are reasonable noise levels, but they're driving people bonkers because they exceed the threshold of human hearing. You know, they exceed the background noise level by a certain amount, and it just based on what their activity is or what they're trying to do. If they're trying to sleep, you know, a faint little thump from a party a long way away. I mean, you had one recently where it was miles and miles away from Mike's house, and he's hearing this EDM concert come through his window at 2 a.m. He's like, oh my gosh, what are they doing?
Yeah.
But yeah, when it becomes a nuisance issue, the single number, the decibel value doesn't matter so much as the human response. So that is an interesting point as well.
Yeah, I mean, I live in a college town, a neighborhood right next to the university, and so I keep earplugs next to my bed. And I don't have to worry about the parties next door.
Well, it's awesome that that you've been, your experience, so that we could probably spend another hour literally just chatting your ear off and listening to everything and all your experience. What would you suggest to a college kid, a high school kid who's just kind of coming up and to find their footing in your world in industrial hygiene? Or
Yeah, I think it's in general, occupational safety and health is a great career field. It's in very high demand. It has some very inherent rewards to it because you are working with people and trying to protect them, and it could be from noise, it could be from chemicals, it could be from other stresses on the human body that's related to ergonomics. It could be some environmental contamination, that kind of work. So there's a lot of reward in it because you're actually doing something that provides a benefit inherent to the work. Certainly, you're going to get paid for it, which is why we work. We have to earn a living, and so if you're going to earn a living, I think it's a great field to go into because of that. Helping take care of other people. I think it also, if you are already inclined to STEM, that this field is probably the most multidisciplinary STEM field you can get into in terms of industrial hygiene, because we deal with anatomy, physiology, toxicology, psychology. We're also doing a lot of math and physics and chemistry, and then we take all of that and apply it through engineering principles. And so really it's a very much multidisciplinary Swiss Army knife STEM discipline, which means
awesome.
You don't get bored.
Yeah, it seems really cool.
I learned so much from you. I mean, honestly, it's like, this is probably for me personally one of the most gratifying interviews we've done. I've learned so much about it. I thought I knew, and I knew nothing. And it just sounds so much about so much. It's pretty awesome. That's awesome.
Yeah, I have one last question for you, at least for me. What is one of the most interesting occupational hazards that you've come across that people wouldn't think would be a hazard? What is there one of those that you're just like, this one's going to surprise you? It's crazy, but it causes a hazard.
Yeah. Okay. So I think the weirdest one I've come across is the use of nitrous oxide in dental work. That nitrous oxide is a teratogen, it causes birth defects, regardless of the gender of the parent that it is exposed to. So you could have a male or female dental hygienist or dentist that's getting exposed to waste nitrous oxide during surgical procedures. And that can cause birth defects in their children.
Wow.
Usually teratogens are going to be one gender or the other, tend to be specific, but nitrous is both. And so Fortunately, now we've designed scavenger systems so we don't get waste anesthetic gas in the surgical theaters. But
That's laughing gas, right?
Yeah, it's Pronox and all that stuff, right? Nitrous oxide. You're telling me like that can create.
Oh my gosh, I had a filling done earlier this year, and they asked like, do you want the nitrous oxide? And I said no, and now I'm really glad I said no.
Wow.
Yeah, well, it is from chronic exposure. Over and over again, day after day.
So
you're not
yeah,
needing
tell
that
me
many
about the
fillings.
risks. Like one filling, like you're okay, but if you're working there, then it's a
with a lot of these chemical hazards, it's that chronic, repetitive exposure that
it's years of
causes it.
exposure to
so
it.
the people working there.
Yeah.
Yep.
Well, thanks for coming on today. We appreciate it. Is there anything else you want to share with the guests before we let you go?
No, I'll just give a final pitch for the field of industrial hygiene. We need more. We need more folks. Take a look at schools that are ABET accredited. That's the accreditation board for engineering and technology. It's mainly master's degree. There are a couple of schools that have bachelor's degrees in industrial hygiene, but there's about 27 that offer master's degrees, and a couple of them do offer online, and they're actually very legitimate, good schools. I'll give a shout out to Montana Tech, even though I'm not a graduate. They're doing a nice job with online learning for industrial hygiene.
Nice.
And of course, where you went, we can give a shout out to them as well.
That's OU Health Science Center, the University of Oklahoma Health Science Center in Oklahoma City. They're working on an online program. I'm on their advisory board as well. And for an undergraduate degree, Oklahoma State University, fire protection and safety engineering technology is a fabulous choice.
Awesome. All right.
Awesome.
Well, thank you very much for coming on.
You're welcome. It was a pleasure.